Welcome back. Let's continue with our lecture on mathematical methods. We have been looking at the contour integrals, especially residue theorem. We have used the residue theorem to evaluate integrals of real valued function. So this is a part of a course PH3103 at IISER Kolkata. We will look at the more contour integrals and their application to evaluate the principal values of a real valued function. So let's look at functions with the singularities on x-axis. So far we have evaluated the integrals of real valued function which are continuous on the x-axis. That is, when we take the complex valued function f of z is equal to p of z by q of z has a no singular point on x-axis. How this would change if there are singularities on x-axis. So let's look at this. There are techniques using the indented contours. We can evaluate the principal value of the integral from minus infinity to plus infinity f of x dx by residue theorem. To evaluate the integral by residue theorem, which has a pole at z is equal to c, where z is a real number, we can use an indented contour. Briefly explain what is indented contour with this diagram. We have several singularities of function f of z in the complex plane. In the earlier case, we have avoided functions which has a singular point on x-axis, but in this case we consider there is at least one singular point or pole, simple pole on x-axis. In such case we cannot use our earlier method in which we have taken the integral along the real axis from minus r to plus r, because we have a singular point at z is equal to c. So we have to use a technique of a indented contour. So in the case of indented contour, you use a semicircular contour c of r centered around z is equal to c and oriented in the positive direction. That is, we cover up this singularity on real axis using a semicircular contour c of r with the radius r and origin at z is equal to c, and then we proceed with the taking the integral from minus r to all the way till the contour, and then use the circular arc to avoid this singular point, and then come back to the real axis and continue with the value of integral. So this is essentially is the technique of indented contour. We proceed as before using this. Important point is to evaluate the integral of this function on the contour c of small r and take the limit r going to 0. For the outer contour c of capital R, as r going to infinity, every time we had to evaluate and ensure that integral goes to 0 before using the method. But in this case, we have a theorem. Suppose f of z as a simple pole at z is equal to c on real axis, if CR is the contour defined by z is equal to c plus r into e power I theta, for theta going from 0 to pi, that is a half circular arc. Let's describe this with the diagram. We have a point z is equal to c on a real axis as a simple pole, and then we consider c of r, a circular arc centered at z is equal to c with the radius small r. Then we take the limit, the small r going to 0, and evaluate the contour integral of the function along CR, and then show that the limit r going to 0, integral along the contour CR f of z dz is equal to pi into I into residue of f of z at z is equal to c. In the residue theorem, we have a closed contour. In this case, we are using only half circular contour and then taking the limit r going to 0. That is why we have a pi times I into residue of f of z at the z is equal to c. Let's try to prove this. Since f of z has a simple pole at z is equal to c, its Lorentz series can be expressed as f of z is equal to a minus 1 divided by z by c plus g of z. Here a minus 1 is the residue of f of z is equal to c, and g of z is an analytic function at z is equal to c. With the convention of Lorentz series, we know that if the function has a simple pole only, then there is no negative powers higher than z is equal to minus 1. So we have the series terminates at z is equal to minus 1, that is a minus 1 divided by z minus c plus g of z. Let's evaluate this integral by substituting the f of z with the Lorentz expansion which we have done. Integral over the contour CR f of z dz is equal to minus a minus 1 integral 0 to pi into I integral 0 to pi I r into e power I theta divided by r e power I theta d theta. The second term which is coming from the g of z is I into r integral 0 to pi g of c plus r e power I theta d theta. The first term we can call is that I1, second term we call it as a I2, and individually evaluate this integral. Let's look at the first term which is I1 as a minus 1 integral 0 to pi. Then we simplify, it takes the simple form of 0 to pi d theta, and its value is pi I into residue of f of z evaluated at c, because a minus 1 is simply the residue of the function at z is equal to c. So we have got the required result. That means somehow we have to show that the I2 have to be 0. So let's look at that too. Let's look at term I2, which is I into r integral 0 to pi g of c plus r e power I theta into e power I theta d theta. We know that the function is analytic. If a function is analytic at a point z is equal to z0, we can always construct a small neighborhood around z0 such that the function is bound inside the neighborhood, is a condition for the analytic function. If the function blows up, then it can't be analytic in that neighborhood. So this essentially reflects as existing the upper bound for the function in a small neighborhood if it is analytic at a point z is equal to z0. In this case, z is equal to c, which is on real axis. So we have a bound for the integral from 0 to pi g of c plus r e power I theta d theta should be always less than or equal to a number m. Now I2 comes as a IR into m, or I2 always have to be less than or equal to IR into m. Now if we take a limit r going to 0, we get I2 to be 0. It is rather straightforward once we have this use this result. Now we have a limit r going to 0, integral of contour C r f of z dz, that is I1, is given by pi into I residue of f of z at z is equal to c. So this is the result which we are interested. One of the advantage of this result is that once we have to use the indented contour, we know the value of the integral, we can straight away use this theorem. However, in the case of outer contour, that is which we take all the way to infinity, there every time we have to evaluate and ensure that it goes to 0 as limit r going to infinity. Let's look at a quick example. In this case, evaluate the Cauchy's principal value, integral from minus infinity to plus infinity sin x divided by x into x square minus 2x plus 2. So this is the integral which we have to evaluate clearly. The complex function which we would like to study is e power I z divided by z into z square minus 2z plus 2. Now clearly The alpha term in this case is 1, which is coming from sin alpha x. So we simply have e power I z as our function. We see that the f of z has 3 simple poles at z is equal to 0 and z is equal to plus or minus I. So since there is a one singular point on a real axis, so we will have to use the indented contour for evaluating this integral. So we essentially try to avoid the simple pole at z is equal to 0 and consider the contour which include the singularity at z is equal to plus I. Let's look at the figure. Here we avoid the singularity at z is equal to 0 using the intended contour CR. We have simple pole at z is equal to 0 and one more singularity along the positive imaginary axis is at z is equal to plus I. Minus I is not along the positive imaginary axis, so only plus is what we need. Now we avoid the simple pole at z is equal to 0 using the contour CR or minus CR because we are going in a counter, going in the negative direction, and then we cover the singularity at z is equal to 1 plus I using the contour C capital R, and we ignore the singularity at z is equal to 1 minus I. We start our contour from minus capital R, go all the way till minus small r along the real axis, then we deviate along the contour CR to avoid the singularity at z is equal to 0 and reach plus r back to real axis along the contour CR. Note that we are moving along clockwise direction on the curve CR, that is why we have a minus sign there, and then from plus small r we proceed to capital R along the real axis, then from plus r we reach back to minus r along the circular arc C of capital R, and that C of capital R should include the singularity at z is equal to 1 plus I, and we take the limit capital R going to infinity, small r going to 0, and then we use the earlier theorem to evaluate the integral. Let's once again look at this integral. Integral along closed contour C, f of z dz is equal to integral along closed contour C e power I z dz divided by z into z square minus 2z plus 2. This integral have to be evaluated along the contour C given in the figure. We know that the value is equal to 2 pi I times the only residue inside the contour, that is the residue of z at z is equal to 1 plus I. The contour C can be split exactly into 4 terms. The first term is along the real axis from minus capital R to minus small r e power ix dx divided by x into x square minus 2x plus 2. And then the second contour is with the negative sign along the circular r CR e power I z dz divided by z into z square minus 2z plus 2. The third term is again along the real axis from plus r to plus capital R e power ix dx divided by x into x square minus 2x plus 2. The last term is coming along the circular R capital CR e power iz dz divided by z into z square minus 2z plus 2. And the results of this is 2 pi I times the residue of f of z at 1 plus I. Let's carefully look at the value of each of these integral. It is easy to show that in this case this integral will go to 0 because in the numerator we have a z to the power 3 eventually resulting in the r to the power 3, and r going to infinity, this term would make the integral going to 0. Now from the earlier theorem, we have this term resulting in the value pi times I residue of f of z at z is equal to 0, the radius of r, small r, going to 0. Then we have left with the two terms which can be combined as a limit small r going to 0. This takes the principal value of the integral which we are interested in. It should be e power I x, not sin x. So this is the integral which we are interested in. So we need to evaluate the residue of the function f of z, that is equal to e power I z divided by z into z square minus 2z plus 2 at z is equal to 0 and at z is equal to plus I. We can straightforward evaluate the residue at z is equal to 0 and it turns out to be half. Well, I will say you can also evaluate the residue of the function f of z at z is equal to 1 plus I and it turns out to be minus e power minus 1 plus I divided by 4 into 1 minus I. Once we have the residue, the principal value of the integral from minus infinity to plus infinity e power I x divided by x into x square minus 2x plus 2 dx is given as pi times I divided by 2 plus 2 pi I times the residue of the f of z at z is equal to plus 1. One can evaluate this, and so the integral from minus infinity to plus infinity cos x divided by all these terms can be the real value of the this residue that we have obtained. Same way we can obtain the sine term too, taking the imaginary of the integral which we obtained using the residue theorem. So one can simplify this further, but I will leave it at this stage. It is just simple algebra to calculate the real and imaginary part. There are some simple tricks one can use it. At this stage, those are not really important. Our goal is to choose the contour and evaluate the integral, not compute some functions of complex value. But that can be done. Now, there is an homework problem which also makes you think a little bit. So you evaluate this integral, which we have already done, you might say, but I want you to do it in a slightly different way. I want you to use the contour given in this figure, where the indented contour you use not as given by the theorem, but in the opposite direction. So now you are including the both singularity at z is equal to 0 and z is equal to 1 plus I. You have to sum both this singularity, but somehow only half value is incorporated in this case because we are including. So I want you to work this out and see if the result is same or different. If it is same, then you can compare whether this also is a viable method for evaluating integral. If it is different, then you got to tell why it is different and why this cannot be used to evaluate the integral.